Alrighty, so Dalton's Law is our almost last law we're learning, okay? So let's go in order. Let's go in ABC order. What was the law that started with an A? Avogadro's Law included what two variables? Moles and meters, yeah, moles. Which one was a B? Boyle's Law included pressure and volume. C? Charles's Law. P12? Virginia Tech include volume and temperature. D? Dalton's Law, okay? So then we'll go through the rest of them. So Dalton's Law is just, it's called the Dalton's Law of partial pressures. Pretty much, it's a summation. Everything, all the partial pressures of the atmosphere. Every little gas causes a certain amount of pressure. If you add up all the pressures of the little gases, you get the total pressure. That's it. So, partial pressure is literally saying like P of, tell me one of the gases in our atmosphere.
Nitrogen.
Nitrogen, so there's a lot of nitrogen in our atmosphere. What else? Oxygen, what else? Carbon dioxide?
Methane.
A little bit of methane, but that's more of a greenhouse gas that's in our atmosphere in minute amounts. Let's stick with like our majority. Oh no, we got that. It condensates on everything. Water vapor, and there's also actually a significant portion of argon. Just BT does. Okay, so what you would do to get P total is our atmospheric pressure. You would take the partial pressure of nitrogen. When you write it like a little subscript, it makes you seem like a very knowledgeable chemist. You're like saying partial pressure of nitrogen plus partial pressure of oxygen plus partial pressure of carbon dioxide. Guess what? Plus partial pressure of water and partial pressure of argon. It's just a summation. So if I told you our P total is our atmospheric pressure, what's our normal atmospheric pressure? 1 atm, right? So 1 atmosphere. And I told you, nitrogen made up like 0.7 atmospheres. Oh my gosh, I'm not going to go through. I gave you numbers here, here, here. I could give you numbers for all of those first 4 gases, and then I could say, what's the partial pressure of argon? AKA sulfur X, right? So basically you would have lots of information about these partial pressures here, and this, what it's equal to, and you would just have to subtract from sulfur X. So it's just a summation one. I think this one's pretty easy. Thumbs up when you understand Dalton's Law. It's a summation. Okay, we're going to do a lab with that in a little bit, but on the lab, there's one thing I have to tell you before. Basically, anytime you collect gases, and you collect them with water involved, water is naturally always evaporating, right? All the time it's evaporating. Not very, like, at a fast rate, but it's evaporating. So the water vapor from our lab will have to be included in our total pressure, which we'll get to in a little bit, okay? So I'm going to skip through the Dalton's Law lab. I'm going forward. Okay, cool. So that's that. Okay, Graham's Law. So we did A, B, C, D. We don't really have an E law. G, Graham's Law. Okay. Yes.
Dalton's Law, inverse or
It doesn't have one of those. Well, I guess you could say it's more directly related because as you have more partial pressures, the total pressure increases. There's no variables in which you're comparing. It's just partials versus the sum. So I'm not going to say they have inverse or direct. Okay? Good question. All right, so Graham's Law, the rate of effusion. What was effusion again? Effusion. It's not diffusion. Yeah. All right, so it's escaping of a gas through a tiny hole, right? So escape of a gas through a small hole in container. Okay, it's basically diffusion. Things are moving from a high concentration inside the container to the outside the container, which is a low concentration, but it's just in a specific scenario of a small hole in the container, right? We've all experienced this because we've had, for example, a balloon that didn't make it past, a week after a birthday or something, okay? So we've all experienced this. And we talked about this earlier. We talked about how energy, kinetic energy of molecules is equal to 1/2. Do you remember this formula? Dealt with mass and velocity. Anybody? M times V squared. Good. So what do we say about heavy molecules? Heavy molecules do what? Move slow. So if you increase your mass, you decrease your speed, aka your velocity, because they're inversely related, right? So this, what we talked about already, is basically what Graham's law is, so you're slightly familiar with it. So Graham's law is the rate of diffusion of any gas is inversely proportional to the square root of its molar mass. Okay, there's a bit more math involved. There's a little calculation with square roots and stuff, but basically, the speed is inversely related to its mass. That's exactly what we had said when we were talking about this formula. Okay, this is not Graham's law formula though. This is called the kinetic energy formula. So Graham's law formula is, I'm gonna write at the bottom. Can I scroll down? Okay. So you can see it's the rate is inversely related to the square root of its molar mass. So I'm going to show you how that works. The rate of diffusion is inversely, so fraction, right? Inversely related to the square root of its molar mass. So this is exactly from the definition. The rate of diffusion is inversely related to the square root of its molar mass. Now, I'm going to say this is the rate of A. So this is gas A, so this is molar mass A, whatever the gas is. Now, most of the time we don't compare, we're not concerned about the rate of one gas. Most of the time we like to compare things. So we're going to start comparing gas A to gas B. So maybe helium to hydrogen. Which one moves faster? Well, based off of your knowledge, hydrogen weighs what? Periodic table. Hydrogen weighs what? Hydrogen gas is diatomic, right? So hydrogen gas is going to weigh what? 2.016. And helium weighs, look on periodic table, about 4 grams, right? So who moves faster, hydrogen gas or helium gas? Hydrogen gas, because it's going to be lighter, right? So there's a version of this where you do a comparison. And so it's rate of A rate of A over rate of B equals this, but we're going to complete the circle. We're going to put molar mass on top and bottom, but realize it's still the inverse and it's still the square root, so that we have rate A, molar mass A down here, and then this rate B is on the denominator on this side, so it's on the numerator on this side. So basically, if you ever have two gases involved and says which one, how much faster does this one move, or what's the rate of hydrogen versus helium or something like that, you're going to use this version of Graham's law. Okay, and I always put the lighter one on top. Okay, that makes sure that your values when you calculate them are like 1.0 or something like 4 times greater. So it's an integer that makes sense, because if you put it on the bottom, you get like, oh, this gas is 0.0065 times slower or faster. You're like, what does that mean? It's easier to say it's twice as fast, something like that. So your math comes out in a better way if you put the lighter one on top. All right, let's do 2 problems. Ready, Freddies? Okay, what is the relative velocity rate of hydrogen gas to carbon dioxide gas? So which version, the first version or the second version am I using? Second, because it's comparative, right? So here's my general formula. Rate A over rate B is equal to square root of molar mass B over molar mass A, right? So I just put the square root of the whole shebang. So who am I going to call A? What was my rule? The lighter one. So who's A? Hydrogen gas. Okay, so this is rate of hydrogen gas over rate of CO2, right? Because that's going to have to be my other one, is equal to the square root of what is going on top here? Of carbon dioxide. Okay, so 12 plus 16 plus 16. 44, good. So this is 44 grams per mole. So that was what I just kind of like looking upward. The carbon dioxides go here. The hydrogen gas goes down low. What's that one? We just talked about this. 2.016, right? This is extremely accurate and specific, so I'm just going to record all those decimals. That's okay. So it's just 2 times, it's basically 2 grams per mole. Okay, so let's see what kind of the math we can do in our head. There's probably not much here, but essentially we have rate is equal to square root of 44 over 2. Well, 44 over 2, isn't that square root of 22? Yeah? So 44 divided by 2 is 22. So this is basically the square root of 22. I have no idea what that is. Calculator. Like 4 point something. Square root. How do you square them? 4.69. Okay, so when you just write that number, you're not fully explaining the answer. So the way I would like for you to write out your final answer is, who moves faster? Hydrogen gas. So you would say hydrogen, it fuses 4.69 times faster than CO2. That's like a one-sentence summary of what you just did. So hydrogen gas diffuses 4.69 times faster than CO2. All right, let's do one more. Told you this last bit of notes were fast. But this will be kind of like your last two formulas from gas laws, and you guys can start practicing here. Okay, this one. We're going to determine an unknown gas, okay? So we're going to be given information that's different than we were given previously. An unknown elemental gas. Now when it says elemental gas, that means it's a gas from the PTOE. So you're looking in the non-metal section on the PTOE whenever you're given something like this. It diffuses 4.5 times the rate of krypton gas. Okay, so who's faster, unknown or krypton? Unknown. So when I start this, I'm just going to go ahead and write rate of the unknown is going to be on top because I already know it's lighter because it's moving faster. Over the rate of who? Krypton gas, okay? What was the rate it told you right here? 4.5, right? It says the unknown gas diffuses at a rate of 4.5 times faster. So this rate, when you compare them, is 4.5. Okay, that is the solution, but now we have to start looking at the masses here. What is the molar mass of the gas? What's the identity of the gas? Okay, so I'm just going to put the 4.5 here, but I'm looking back over here as I write my molar masses. So this whole thing is equal to the square root of who over who. So the molar mass of krypton over of unknown, right? So which of these is really our question? The molar mass of unknown, right? Yeah, what's up?
Doesn't the unknown go on top because it's faster?
It's fast, yeah, that's what I did over here. So remember, whenever you do your inverse relationship, the top one goes down low here, and the bottom one goes up high here. So it goes on top of the rate, yeah, good question, or good point. Whenever I say it's going on top, it's going on top of the rate, not the square root part of it. Okay, so then I'm going to plug in my numbers I know. I know the molar mass of krypton is what? What is it? 83.8 grams per mole. And mass of unknown is I'm going to call X, because I don't know what that is. All right, so basically your math involves you going, okay, 4.5 is equal to square root of 83.8 grams per mole over X. How do I isolate X? Square everything. Okay, so by squaring everything, you say 4.5 squared, I'll calculate that in a second, is equal to, I've now taken away the square root, so it's 83.8 grams per mole over X. Okay, keep going. How do I isolate X? Multiply. So take my X on both sides and multiply. So that's 4.5 squared times X is equal to 83.8 grams per mole. So what's 4.5 squared? What is it? 22? Okay, so this is 22. 4.5 squared is 22. 20.02. I hear you now, sorry. Okay, that's right. I'll just do it myself. just checking. 0.25, okay. Okay, so there's our 4.5 squared. So you're just going to divide by 20.25 on both sides. So X is equal to 83.8 divided by 20.25. 4.13. What units is this going to be recorded in? 1.4. My bad. Grams per mole, because it's molar mass, right? So, question 1 has been answered. You got the molar mass of this unknown gas. So what is the unknown gas? Look in your periodic table. Who's closest? Helium. There you go. This is helium. You're just basically looking at the mass of whoever's closest to 4. That's helium. Alright, so those are basically the two types of problems you would have with Graham's Law. I could give you something and say find the rate, or I could give you the rate and say find the unknown gas. Something like that. Alright? So why is this important? Who's ever been to the Macy's Day Parade? Meaning I haven't. So one person. Wow. Okay, oh no, I'll show you this in a minute. Oops. Okay, so why is this important? Because if you don't know information about Graham's Law, this 400,000 bunny, it will make it to the parade. And then all the parade goers are going to be so sad. Think of all the children they disappointed when this happened. Right? They got to get on that chemistry. So now they have like engineers and chemists and stuff that help them with the parades. They don't want this disaster to happen again. Right? Don't you feel bad for those kids? People. Okay. Have a heart. Okay. So let's go back to the lab. Okay. So get a piece of paper out. Call up the one I'm speaking about. I'm going to show you how to set up in this video because this lady made this video and it's really good. I'm just going to click through a little bit to show you the important steps. Okay, so this will be a quick lab, and then after that, you guys can ask your question on class at 14, work on it in your desk, whatever you need to do. Basically, you guys are going to have your safety glasses on, you're going to have an upside-down graduate, or you'll have a graduated cylinder, and you'll have this pneumonic trough, which is this thing right here. Basically, it's a container. The container is deep enough that you put your hand underneath, and like it's filled with water, you can put your hand in it. So if you have small hands, you're probably the one that's going to be putting your hand in the water. The graduated cylinders will have the plastic stuff on it. You'll have to take that off before you begin. And I'll show you at the very end on how to dispose of the butane gas, because butane gas is flammable, and I like to light matches in my free time, so I'd rather not burn the house down, okay? So, during the lab, I'll have you guys write down some of these pieces of information, and this will P gas plus P water. So I'll get to that shortly. But let me show you the basic setup, and then you will be set free. Okay, so... So basically, you're going to dip your lighter. You have a butane lighter. You're going to dip it in water because it's going to be in water at the end of the experiment. So you want to have like kind of a controlled situation. You're going to dry it off, but there's still water in the crevices, and that's okay because after the experiment, there's going to be water in the crevices. So basically, you're setting it up so that you don't have any mass difference according to water. You'll mash your lighter. Sorry, she's kind of slow. She's like, let me show you how to mash the lighter. Okay. You'll mash your lighter, write it down. Then you'll have a graduated cylinder. You're going to fill it up to the very, 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 very top. She did not fill it up to the very top, okay? To the top. And then after that, once you fill it to the very top, you're basically going to, here's your graduated cylinder, okay? Got it? This is a graduated cylinder. And there's water in it. Filled to the very brim, overflowing, okay? You're going to put your hand on top, and then you're going to invert it underwater, because in the water, you're going to have a full column of water in this graduated cylinder, okay? If you have any bubbles whatsoever in the graduated cylinder, your gas volume is going to be off, and you'll have percent air in the end. So if you flip it and you make a little oopsie and there's a bubble in it, redo it. It might take you 3 times. It's okay. But get that started ASAP, okay? Because after that, once you get your graduated cylinder filled with water in there, no bubbles at the top, you're going to then hold a lighter. Hold on. She's real slow. Okay. So you're going to put your hand, what I would do is one person do this, hold the graduated cylinder, put the lighter underneath the mouth of the graduated cylinder, which is underwater, and release the gas into the graduated cylinder. Because now these lighters, they don't have the flint on them, so if you just strike the lighter, there's just going to be gas going everywhere, okay, and we won't know it. So if you strike it, it won't catch on fire, because Mr. Smith said I had to take the flints out, so I did. But the gas will go in here, okay? You eventually will collect gas in this graduated cylinder. All the water will be pushed out because the gas is pushing it out, right? But the graduated cylinder is a 100 milliliter graduated cylinder. So if you go above the 100 mark, aka it's upside down, so if you go below the 100 mark, you will have no idea how much gas you've collected, okay? So please do not go above 100 milliliters of butane gas, because then you'll have air and you won't know how to account for it. So you're going to do this until it's, your water level inside of the graduated cylinder is equal to the water level of your bowl. And that means you can assume something very special. You can assume that the gas inside of the graduated cylinder, so it's like this, there's gas up here, you can assume P gas, and the water vapor that's in here is equal to the pressure of the atmosphere outside. only when the water level outside of the graduated cylinder in the beaker is equal to the water level inside. Okay? So if you get to that point, you have to assume that this plus this is equal to P atmosphere. And then you ask, well, what's P atmosphere, Miss Enlow? Well, on the day like today, looking on the American Weather Channel, they like to publish in inches, because we're Americans. So this is what you need to have. However, you need to convert it to a usable unit like what? Millimeters of mercury, and then probably atmospheres, but it's up to you, okay? So let's do 3 people per group. You guys ready? It's called Molar Mass Butane Lab. Let's go. Hold on, 1 second. 1, 2, 3. Hold on, you guys, you 3 go to the last issue. Come on, do this all by actually, sorry, I thought I had 2. Yeah, okay, if you guys are 4, then let's go. In the last session, you guys go to one of these. Okay, so I'm putting Alright, please come get your safety glasses. You have 45 minutes to get this accomplished. The bowl? The bowl? Yeah. Yeah, that's like the water container. That's a graduate cylinder.
That's what I thought.
That's what it is.
I didn't know if that was just like that.
It's like a bowl you put your hand in afterwards.